Okay, so in this video, I'm really going to talk about the bigger picture of topology, really the essence of topology, what the topology is all about. Okay, to really understand, like this is stuff fully that I'm going to talk in this video, I would like to highly recommend to, watch some of the previous videos where we kind of talked about strange topological universe, when two objects in that strange topological universe are equivalent and when they're not equivalent. So let's set up some terminology for this video. So whenever I would say the word object in this video, you have to kind of treat the object as anything around you, anything physical around you actually. Okay, so it could be a cup, it could be a table, it could be your pen, it could be anything actually. Okay, could be a line, could be a circle, anything around you. By object I would mean this. Okay, and by continuous transformation. Okay, I've said it before, but let me say it again. By continuous transformation, I'm gonna mean, stretching an object, shrinking an object, folding an object. Okay, or so it's like doing anything. Okay, so it's like doing anything without breaking or tearing or gluing that object actually, and gluing the parts of that object. Okay, gluing the object. Okay, so any operation of stretching, shrinking, extending, folding, do anything. Okay, but keep in view that you're not allowed to break that thing, tear that thing, glue that thing actually. So that would be the meaning of continuous transformation. So continuous transformation of an object means pick a cup, for example, and stretch it, shrink it, fold it, but don't break it actually. Okay, that would be the terminology that I'm going to use actually. So what is topology? Okay, so what is really the science of topology? I mean, in its essence, it's really a way of thinking actually. So it's so topology is basically a way of thinking about objects, and by objects, as I said previously, means things that exist around you. So it's a way of thinking. So what do you mean by the way of thinking? In other words, you can also say that it's really is about looking at objects, in qualitative manner actually. Okay, in qualitative sense. All right, just like if you have for example, if this is you, okay, and you, for example, wear these topological goggles. Okay, these topological goggles will give you kind of another very interesting way to look at the things around you. Okay, and what is that way? Okay, or what that way is all about. So the topology is all about roughly asking two kind of questions. Okay, so asking two questions. and the answers of it actually. So topology is basically try to find the answer of two questions actually. So number one, what is the fundamental structure of an object? So you pick an object, what is the fundamental structure of it in the qualitative manner, in qualitative sense, not in the quantitative sense actually. Okay, that's the first question that this addresses. So I'm going to talk about these questions in a more of illustrative way in a moment actually. And the second question, the interesting question that the topology tries to ask is basically that, okay, what are the properties, okay, of objects when you're looking through topological goggles, okay, that are invariant, that is not going to change. Okay, so what are the properties of objects that are not going to change when you transform them through? Okay, so when you transform them through continuity. Okay, continuity. So topology is all about asking the two questions. So what are really the fundamental structure of an object, and what are the properties? The second important question that it answers is that what are the properties of the object that are not going to change when you transform it through continuity. So let's try to illustrate now like these questions and answer these questions through some illustrations actually. Okay, so previously we kind of talked about a strange universe in which roughly mostly we talked about, for example, a line. Okay, and then we saw that if you apply kind of a continuous transformation onto this line, you can turn it into a curve. You can turn it, for example, into a spring. You can turn it into a parabola. You can turn it into any kind of curve you like actually. So the curve actually. Okay. So all these objects are topologically equivalent. We have talked previously about it. And the other category of objects, for example, if you take what do you call a circle, or maybe a triangle, okay, or a rectangle, or any closed picture actually. So take all closed pictures. So we know from our previous video that in a topological universe, in the straight universe, all of these objects are equivalent actually. So what do you mean by equivalent? That I can apply some kind of continuous transformations onto the circle. So you can do stretching and shrinking and do something, and I can turn it into the what do you call a triangle or a rectangle or this picture actually. Okay, so now so what the topology is basically all about. Okay, so topology is about talking about the properties of the object actually. So what are really the fundamental properties, for example, of a line? Okay, so what are the fundamental properties of the line actually? For example, you can ask several kind of questions. Is length a fundamental property? Okay, is length a fundamental property of, for example, line? That the answer is that no actually. Okay, the answer is no, because if you, for example, continuously transform a line and it turned it into such a curve, for example, this curve can have more length than what do you call this line, or maybe the spring can have more length than what do you call this line actually. So length can't be, for example, a property, okay, an invariant actually that is preserved under the continuous transformations actually. Okay, similarly, you know, for circles, triangles, and all this, you can say that the area is a property that is not that is not invariant under the continuous transformations actually. So you can, you know, create equivalent. So for example, the circle is topologically equivalent, okay, by applying continuous transformations. You can turn a circle into the triangle, but by doing it, the area is not preserved. The area might be, you know, different actually, the area of this. Though they are equivalent, but their areas are not, you know, same actually. Okay, so it's like an area, length, and area, you know, and several other properties like are the quantitative properties actually. So these are the quantitative properties of the objects, and in the topology we're not interested in the quantitative properties of the object. For example, we are interested in a more of the qualitative property of the objects. So what could be the, for example, some of the qualitative properties of you know, for example, line actually. Okay, so one of the qualitative property of the line could be, okay, you can pause the video and think about it. So, I mean, one of the qualitative property of the line could be that it is, for example, finite in some sense. It's compact in some sense. What do you mean by that? So it starts from somewhere and it ends somewhere. Okay, so it starts from somewhere and it ends somewhere. You can start from here and end here. Okay, and if you continuously transform, for example, this line, so I transform this line, it turned into the curve, that property is still there. So it has, for example, you know, it has a starting point and an ending point actually. Okay, so it's like it's finite in its nature actually. Okay, it's finite in its nature, it's compact in its nature. For example, you know, like this guy spring also has what do you call a starting and an end, and this parabola has a starting and an end, and this curve has a starting and an end, for example. So this property of, you know, a finitude actually. Okay, so it's like a finitude are, you know, a more, you know, technical way to say it, the compactness, okay, of the line is kind of a property that is not changing when you are even transforming it through continuous transformations actually. Okay, so it's compact actually. Okay, we're going to define all these things in a more technical way later on, but you know, it's finite in some sense. Okay, so that's one property, for example, that is not changed when you are changing the line into what do you call other curves using the continuous transformations actually. Okay, so that's one property. How about some other properties? So the other property could be, for example, I mean, let's talk about, for example, that if you see, you know, in this line, for example, there is no hole actually. Okay, in this line there is no hole. So you can say that this is like just one piece actually. This is like just one piece. Okay, or in a technical sense, I can say that like this line is kind of connected actually. So there is no part of this line which is not connected to any other part actually. So all parts are connected to each other. Okay, you can start from any point and you can reach to any other point you can like without getting into the break actually. Okay, so I can say that this line is kind of connected actually. Now, is this connectedness preserved? Okay, so let me write another thing which is connectedness. Okay, so this line is kind of connected. Connected means that, okay, you can start from somewhere and you can reach to some other point without break, actually. Okay, roughly, that's really the rough idea. How about this curve? So you can see this curve is also connected. Okay, this curve is also connected. Spring, there is no break, so it's also connected, actually. You know, the parabola, it's also connected. And this curve is connected. So I can say that if you take a line and transform it through what do you call space, okay, so it's like the connectedness are there, actually. Okay, so first of all, like this finitude and compactness is kind of a property of the fundamental nature of the line that we said that we want to ask, that what is the fundamental structure of an object, actually. So for example, one of the fundamental property of a line is that it's finite, it's compact in some sense, actually. Another fundamental property of the line is that it is connected. Okay, and you see that when you transform this line into the curve, connectedness and compactness, the finitudeness is still there, actually. Okay, that is not going away. Okay, so in the similar manner, you would like to, not only these properties, but there are lots of other properties as well that we will see, actually, that this line have and this curve have, and those properties are preserved when you try to continuously transform these lines into the what do you call curves, actually. Okay, so and these are the properties that are, for example, not going to change when you continuously transform them. Now let's move to, for example, circles, and all these pictures. We saw that areas are not area is not, for example, a topological property. It's not a kind of a property that is not changing when, for example, you're continuously transforming it. So what could be some of the properties, for example, that for example this circle has, actually? Okay, so and we could say that, okay, that property is really the fundamental property of what you call circle. For example, one of the property could be that, okay, imagine you are kind of a bug moving on this line, actually. So imagine that you are a bug. Okay, you're a kind of a bug, actually, all right, which is moving on a circle. Okay, and it starts from this yellow point, it's moving on a circle. So it's like you will keep on moving. So the bug will keep on moving onto the circle. Keep in view that, we may also feel that this circle is big enough. It's like a huge, actually, as compared to the bug, actually. Like for example, the Earth is bigger, hugely bigger than, us, actually. So it's like we are moving on Earth. Okay, so like this bug is moving on this circle. So what is the first fundamental observation that this bug is going to make, actually? So one of the fundamental observations this bug is going to make is that, like, this circle or this object on which I am moving has a property that when I start moving from one point, I can return back to the same point after the finite amount of time. Okay, so in a finite amount of time, I can, for example, start from one point and move around, what do you call this, this entire object, and return back to the same point, actually. Okay, so that's really is the fundamental property, for example, of what do you call this circle. Okay, and this fundamental property kind of also shows that really the circle also has a kind of a finitude, actually, or it also has a kind of a compactness, actually. So it's really the compact. It's a compact object. It's a compact object that you start from here, and in some finite amount of time, you can return back to the same object, actually. Okay. So it has kind of this finitude. So it's not like infinite, actually. So okay, it's not like that. Okay, you started moving and you kept on moving and you never returned to that point, actually, back. So you will return to that point. And you see that that so circle is in some sense what we call compact actually. But let's transform this circle into, for example, a triangle through some continuous transformation. Okay, we know how to do it. Okay. Then the question is that if this compactness is preserved, the answer is still yes, actually. That, for example, you start from some point onto the triangle. You are a bug, actually. Let's imagine that you are a bug moving on this triangle. Okay, so you're moving on this triangle, and then you're moving on this object, and then what will happen. So in some finite amount of time, you will return back to what you call the same point. And the same is the case with, for example, rectangle, and same is the case for any kind of, for example, closed figure actually. So take any closed figure, you can start, you can move, and in some finite amount of time, for example, you can return back to what you call the original point. And that kind of shows that this object, this circle, has kind of a compactness, and that compactness is preserved when you transform it through some continuous transformation actually. Okay, and you turn it into a triangle or a rectangle, or what do you call this picture, this compactness is there. Okay, this compactness is not going away. So it's like, and by compactness, intuitively, it's really a kind of, it's kind of finiteness actually. Okay, it's not really finiteness, but they're close enough to finiteness actually. How about connectedness? So is circle connect actually? So for example, if you are a bug moving on the circle and you start from this yellow point and you return back to the yellow point, is there any point where, for example, the bug would, for example, not find its way, or is there a gap actually? Is there a hole in this boundary of the circular? The answer is no actually. Okay, it's just one piece. So the circle is just one piece. So I can start from, for example, a point, and without a break, I can reach to the same point actually. Okay. How about if I transform this circle into the triangle, or maybe I transform this circle into this closed picture actually. So does this closed picture also have this property that you start from a point and move onto the entire curve and return back without a break actually, without a hole? So it's not like that you have a kind of a hole in the curve actually. Okay, so it's like, because if you have a hole in the curve, the bug would not be able to reach to the same point actually. Again, the bug will not be able to reach to the same point. Okay, so in that case, we will say that connectedness is not preserved. So roughly this is also connected actually. This is also connected. You can say that the circle has also connectedness property. So I can say the connectedness is really the fundamental structure of the circle and anything that is equivalent to the circle actually. Okay, and it's kind of a property that is not going to change when you apply kind of a continuous transformation onto, what do you call, onto the circle actually. Okay. So another way another task actually is really to, you can also think topologically, and you can say that, okay, topology can also answer the questions, for example, that why a line or a curve is different from a circle actually, why they are not topologically equivalent actually. Okay, so they do have different topologies. Okay, they do have different topologies. Why they do have different topologies? By topology, I mean the fundamental structure. They both are fundamentally different actually, these two objects. Why these two objects are fundamentally different, and how can I see it being a bug on it? So for example, if you're a bug moving, okay, on what do you call this curve, what would be your feeling? What you have to do? So just, you can pause the video for a second and, for example, and think about that. If you're a bug moving on to what do you call this curve, and if you're a bug moving on to what do you call this circle, what would be the key difference that you will observe actually? Okay, so one of the key difference that you will observe, that if you are a bug and starting from some point, okay, you can reach back to the same point without returning actually. So without getting back, so you move this way, okay, and without returning, without getting back, okay, you can reach to the same point. While here, when a bug is moving on to, for example, the curve, when the bug would reach here, okay, when the bug would reach here, it's like this would be a kind of a dead end for the bug actually, okay. And if you have to return back, the bug has to flick back, okay, it has to go back actually. While in circle, the bug can return back to the same point without, flipping its direction actually, flipping its direction. And that's what makes, for example, that the circle is not equivalent to, or the circle has a fundamentally different structure than what do you call the circle. A line has a fundamentally different structure than what do you call circle, okay, like, because if you're a bug moving on to it, and you reach to that end, to return back, you have to change your direction and get back and move and reach to this point. While on the circle, you don't have to do it. So it's like investigating. So it's like topology is all about, okay, so roughly topology is all about, thinking from the perspective that think like a bug, okay, think like a bug, think like a bug about what do you call this strange universe in which everything is flexible, in which you can do the continuous transformations actually, and try to find the fundamental differences between the objects, okay, that that if you haven't given, for example, line and this curve, do they have fundamental structure? If you haven't given a line and, for example, a rectangle, do they have the fundamentally same kind of a structure actually? Or do they have, if they are different, what makes them different actually? Right. So this is what really is the subject matter of the topology, that you want to know what are the properties of the object, the fundamental properties of the object in a qualitative manner, looking it into the qualitative manner, and what are the fundamental properties of the objects that are invariant, that are not going to change when you transform them under the continuity. So the topology tries to answer these two questions. What is the fundamental structure of object, and what are the properties that are not going to change when you transform them continuously. Hope you got some essence of this actually, and really all of the topology is making these two ideas. The mathematical topology that you learn actually, okay, prove theorems and do all this, is basically making these two questions, or answering these two questions, are like doing this, dealing with this question 1 and question 2 more rigorously, more mathematically actually. All right, the takeaway of this video. So the takeaway of this video is that topology is all about answering two questions. What is an object? qualitatively. Okay. Qualitatively. So what are the fundamental properties of the object qualitatively? And answering the question, what will not change in object when you continuously transform it. That's it. So these are the two questions that I try to answer actually. All right. And this is what that we're going to learn more rigorously later on in the course. I hope that you got some bigger picture of the topology.